Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
That is probably, as many of you know, it's one of the most creative and interesting computer science I just learned that trees, T-R-I-E trees, were invented by Ed when he was a jet pilot, a fighter pilot in the Air Force. I thought he'd done this as an academic, but no, he was actively in the Air Force at the time and published his fundamental data structure in industry. Ed is also known, there's a quantum computing, fundamental quantum computing circuit named after Ed, and certainly we in computer graphics know Ed through his starting a pioneering prototypesetting company called Live, and later spawned a small computer graphics effort that really one of the most advanced computer graphics effort in the world. It really was one of the main things bringing computer graphics to so Ed has continued to
Thank you. What I'm going to talk about, if my voice lasts, is a set of ideas that have been percolating around in my head for a number of years. And it starts out as wishful thinking. There are certain problems that all of us who use computers encounter, both programmers and ordinary users. And I had sort of the germ of an idea of a way that you could attack these problems in general. And so what's happened is over a long period of time, every time I come back to it, I've discovered maybe some other solution to one of the sub-problems. And I now feel at this time that there's enough there that we ought to start a project to make these kinds of things happen. And I'll explain what these are. Well, let me just, a little history here. Okay. There's this interesting fact about VLSI. When people started to think about it and they began to realize that, you know, there would be steady progress in how much you could put on a chip, how many circuits you could put on a chip, the yields for circuits was always pretty low. So the focus that everyone had was such as, how can we make a memory chip with lots of bits that works despite two problems, one of which many of the memory cells won't work at all. And the other problem was that when they did work, they made errors. So sort of the whole industry was focused on how do you make reliable chips out of unreliable parts. Meanwhile, at IBM Research, a group there called itself the 100% School. And they went against the whole trend, and they had the idea, hey, let's solve every problem that causes circuits to not work so we can make big chips where 100% of the components work. Needless to say, they ended up being right, and the whole world has gone down that path. It's kind of amazing to think about that you actually, on a chip, you get hundreds of millions of parts, each of which is doing something billions, potentially billions of times a second, and everything done is done exactly correctly all the time. That's just a completely mind-blowing fact, okay, in my opinion. Okay, so that's today, right? Wonderful. We've learned something new that we can do with this ultra-reliable stuff. We've learned how to make unreliable systems out of ultra-reliable parts. You know, we're getting so good at this that I consider it something we need to worry about. Okay. Now, you know, it's not just that people make mistakes. Person A can write a program and it's correct, and so it works. And person B writes a program and it's correct and it works. You put them both in the same computer and something bad happens. Okay? That kind of thing. Okay. For instance, one of these pops up. Okay. So I had an experience recently, and since I've been working on this, I've treasured all of my bad experiences. It's made life much more livable for me. Gee, I can collect some data here on what goes on. So something like that pops up every so often. Something like this pops up. This is just sort of Excel telling me some kind of inane choice here. You know, it's, you know, that's just due to a little complexity in program. Nothing wrong with that. Then one of these pops up every so often. Internet Explorer is complaining that something strange happened. Adobe, that's the most common one, is to see something from Adobe that doesn't make sense. Okay. But what happened with me is these guys suddenly started happening more and more often. And then another one would come by. I don't know what line 77 means. Another one would come by. And this is a chronological, I'm giving you these in chronological order. So something wrong is happening all the time, and here's where you'd see one of these. You know, I have Internet Explorer fired up, I want to go to CNN for some reason, and this thing pops up. Of course, if I make it go away, then maybe another one pops up, and I make it go away, and then CNN starts running. Okay. So just funny bugs, okay? So being an intellectual and so on, I'm trying to figure out what this is. And here's another thing. Internet Explorer is complaining about this, Internet Explorer is complaining about that, and then I noticed Outlook is complaining about various things, Outlook complains about this, and this is all in fairly quick succession. So I think this must have something to do with the Internet, or something to do with, you know, everything, just Internet Explorer, Outlook, making errors all the time, and finally a clue comes along. This system called McAfee says to me that some program, obviously something that shouldn't be doing anything, is trying to connect to the Internet, and it caught it, right? Well, I've blacked out what it said, but I'll show you what it said. Here's what it caught. It caught itself trying to connect to the Internet, okay? Bad thing, okay? So what I did was, not knowing anything, I expunged McAfee from my computer, and all problems were gone, just like that. Okay, so now what I want to do is to see a big project that fixes all kinds of things like that. Okay, I mean, now, you see, the normal thing that goes on is, and Carnegie Mellon, for instance, is involved in something called dependable computing with places like NASA and a lot of other universities. There's a lot of effort at how to write program properly. You know, some magic way you write it so now it's going to work, and so on and so forth. I think all that's well and what? 100%. Yes, in some sense. But here I think it's not misguided, but it's good for people to write programs better. But I don't think it will solve the problem, to be honest. It'll solve some other problem, maybe. Okay, so what I'm trying to do is get a big project going. That's sort of the meta issue here. Have a project going that can work on these things. You know, we have to find some funding for all this, collaborators, some, you know, way to make all this happen. When you have some big idea that might involve lots and lots of people working, you know, you start out doing what I'm doing. You start talking to people about it and see where you can get with that. Okay. So there's this thing called computer consciousness. The idea is that the computer should be aware of what it's doing and why it's doing it. Okay, and the system I figured out requires that CPUs be made with a few additional capabilities in order to help the system run. So the idea is that CC, you know, when you click on an icon, computer consciousness has in mind what should happen, and it keeps its eye on what is happening, as it were, and sees whether or not it does happen. And the concept is that it should be able to figure out if it doesn't happen properly, why, and do something about it. That's the idea. Okay. So First of all, it's very important that the system be aware of the passage of time. If I click on the icon for MS Word, then that's a kind of first cause, prime cause of some sort. I want something to happen, and it should happen within a certain amount of time. And what should happen? Well, you know, a lot of stuff should happen, but one of the things, as far as I'm the user is concerned, and that's that on my screen up should come what I expect to see, you know. So, and the cause of that would have been that I clicked on something, and so on and so forth. Okay. So, computer consciousness would have the idea of associating that icon and my clicking on it with an event that's supposed to happen within a certain amount of time, and it would, you know, look to see if it's happening. That's the idea. So, amongst the problems is computers forget how to do things that we still want them to do. This happens to me all the time. I'm using any complicated piece of software, and suddenly it's in some mode that's different than I wanted, probably because I typed something without thinking about it or hit a key by mistake or something, and a modal change takes place. There's no error in anything. I'm just, you know, suffering as a consequence because I don't know what I did and I don't know how to get back sometimes, that kind of thing. Okay, so on. So it doesn't matter how much time computers save us. All that matters to most people is how much time they waste needlessly, and so this is an attempt to make problems like that go away. We had a couple of interesting experiences, computer-related, with going to Mars or exploring Mars. The Mars Polar Orbiter, you know, didn't make it. And why? Does anyone know why it didn't? What happened is, Lockheed wrote some of the program and JPL the other, and one of them figured things in, I think, miles per hour and the other in kilometers per hour. And this bug didn't show up until it had to do its final descent, and so instead of having a controlled descent, it crashed. Okay, and that was the end of it. This is a very simple bug. Okay. The Mars rover Spirit, you probably recall at one point suddenly this rover went brain dead on Mars, and no one knew whether they would be able to save it. It stopped communicating, et cetera, et cetera. Eventually, they did save it. Okay, they haven't published what the source was, but I don't think it's a secret. Here's what happened. In mid-course, they decided to upload in a later version of the software. And being cautious about it, they decided to do this in 2 steps. Send half of the software, send the other half, you know, and load in one half and load in the other. In any case, when all was done, they had actually loaded in one half of the software and not the other half. So it wasn't, the fact that some buffer overflowed wasn't because some stupid programmer forgot. It's just that it had half of one code and half of another, and that was the error that ended up showing up first, and so on. And they almost lost the mission because of that. So what I think is that these 2 things, which we'll talk about, computer consciousness and software redux, could have prevented these problems, and if they existed, could have coped with them so that the missions wouldn't be threatened. These were just, this is sort of old stuff. I mean, there are lots of things built into computers that can cause bugs all over the place. I don't want to dwell on that right now. Okay. There's a thing I call a machine understandable comment, MUC. And the idea for computer consciousness is that basically it knows comments for every instruction in every piece of software and for every data word. This doesn't have to be too big of a burden. For instance, if I have an MP3 file, my music, well, the whole file is MP3, and that's all you need to know. It's a description of it. If I have another word, it might be a floating point number, but what we'd like to know is something more about it. What's this floating point number? It might be the velocity of something, the speed, I should say. And another number might be a number of dollars, which is, you know, that's factors, that's a kind of money, that's a unit like mass, length, time, money, whatever. And there are specific kinds of units like kilograms and pounds, dollars and pesos or whatever, right? So these are kinds of facts that, in some sense, some system that's trying to understand and know what software is doing ought to be aware of. Okay. So my idea is that these systems can go on getting more and more complex, but become more reliable in spite of that, or okay, and be less likely to waste users' time. We ought to improve the experience of using a computer. And then speech. This is something I want to dwell on for a minute. This idea of conversing with an idiot, I don't know how many of you have had the problem. Sometimes it comes up when you're talking to American Airlines, but there's nothing worse than speaking to an idiot. Typing to one is much better, there was this point in time where about maybe 20, 25 years ago, where cars started to talk to people and they said, fasten your seatbelt, okay? But you put a package on the seat next to you and it keeps telling that seat, the person, to fasten their seatbelt, over and over again, and, things like that. And the public had a tremendously negative reaction to all of this. All the speech disappeared from cars, and it was replaced by little things that go bong, or something like that. Okay. So, but if you can make something that's smart, then talking to it is a huge win. And what does smart mean? Well, not that it's intelligent like us, but that the subject matter that the conversation is about involves shared information. Okay. In other words, it knows about the thing it's talking about, and you know about it. And then speech suddenly is a winner. Okay. Now, computer consciousness is a set of sort of software, hardware, and other developments that would be part of an operating system. Software Redux is my definition of the task that programmers do that includes everything that a programmer ever does, with one exception. The exception is like this. Someone comes to you and says, hey, I need a program that, will sort a table of the following kind, and they're very big tables and blah, blah, blah. It tells you something. And then you go and start writing a program. Okay? That's where you're writing code from scratch. I mean, you may use libraries and God knows what, but you're writing the code, and what you got was like a natural language, English or something, description of what was wanted. Okay? Now, what percentage of the time of all programmers on Earth is spent doing that? I think it's very small. Okay? We'll get to that. So these two areas are very different problem areas, but they have certain interrelations, and they both benefit from the same developments there. So Software Redux is designed to solve a whole bunch of problems as listed here. Viruses and their relatives is more a problem for computer consciousness. So, okay, here we go. The best way to describe the fraction of work that is writing brand new code is that it's getting vanishingly small. That's the best way to describe it. And okay, these are just some generalities here. I didn't have, I need a little more time making these slides up, so I was working on this morning. Okay. Okay. The two items in red here, designing algorithms and data structures, writing the original code, are the things that Software Redux does not address. But debugging the code, maintaining the code, porting to different platforms, dealing with revisions and so on, and sort of 20 years of what you can call software maintenance are things Software Redux would deal with. Okay. So here's some more sort of propaganda about what computer consciousness does. And part of computer consciousness is, I think of as like an immune system, because there's this fact that's interesting. The way the immune system works, sort of, is when you're an embryo, these little cells go out and familiarize themselves, as it were, with everything in your body. And the idea is attack anything except all the things we're familiar with. In other words, so that all of the processes and cells in your body are not subject to attack unless you have an autoimmune disease or something. And that system works pretty well to defend you against various things. So if you have this computer consciousness, it can learn a lot by keeping its eyes open when things are working right. This is an important point. And so it doesn't have to learn specific knowledge about software because it can sort of come with that knowledge, but about what you're doing with the software and what you expect and like, that's stuff it can learn about. So there's this thing where you expect the system to understand that there's a fundamental sort of prime cause for certain events. If I click on an icon, I expect that program to come up and run, and I expect that to happen within a certain amount of time. So if I click on the icon for MS Word, what we would like is that the system verifies that happened. And this brings up one point about software, computer consciousness. To be aware of what a computer is doing, the system, the software that's running it has to have access to all kinds of things. So it really needs to know what information is going out of this computer on various ports. Here's a better example. If I want to know what the sound output is doing, what can I do? Well, I could listen with the microphone, couldn't I? If something says, go beep, and or if the user does something that means some sound is supposed to come out of the computer. By the way, has anyone ever had this experience? You do something to make some sound come out of the computer and it doesn't come out. I think, this has happened to me so many times it can't be just me, okay? And usually I can fix it quickly, and on occasion it's a long process of hunting about all the, there's so many ways what the manufacturer supplies to control the sound and what the operating system supplies and the particular program supplies and so on. And within it all, somehow there's sometimes, you can get it right quickly and sometimes you can't. But the point is, what I would like is that anytime something wants to make sound, it listens to hear if sound is coming out, this particular sound that's supposed to be made. I don't mind if it's looking at the actual output. You see, we can assume the hardware works because the hardware is so much more reliable than anything else. And you want to have enough checks so you can find bad hardware. But normally, it's in the system somewheres that causes trouble. So you want to be able to have end-to-end checks. Something wants to make sound, do we have sound? Something wants the sound to display, was it sent to the display drivers? Something wants to send something out the printer port, did it go out the printer port? That's an interesting question. You want to know the answer to it, okay? And the system should be able to figure that out all by itself. Okay. So there'll be a lot of repetitive things now and then because I didn't have a chance to sort of go through all this. So if you look at words in computer memory, the words fall into these two categories. The meaning of the word is obvious. Say it's an add instruction. Well, supposedly this program it's smart enough to know what an add instruction is, okay? Then the meaning of the word is not obvious. Well, that has to do with sort of what type is this word, what's it for, and so on. Okay. So we want to have information that solves the problem of what the meanings are. And all these meanings are designed to be put to use so this thing works. What I've found is to make this work right, you need a number of mods to CPUs. And these are things that would help this introspection run well. So, for instance, you could have modes in the CPU where it could keep track of every subroutine call. Just start filling up a buffer with every one that occurred so that it knows what the flow of control was exactly. And keep track of data dependencies and effects. Here, it's something like what's in Excel. In Excel, if you want to, you can click on a cell and it says, lights up connections to all the cells that are part of computing what's in this cell. You can click on it a different way and it says, here are all the cells whose value is a function of this cell. And you want to be able, and this computer consciousness wants to be able to quickly generate the same kind of information. You know, if it finds something that has screwed up, there's a register that has something screwed up, it can do an experiment, rerun things, but this time it can rerun it where it looks to see everything that affects that register, and that helps it do a search for things. Okay. A key thing in software Redux is the idea of being able to have a high-speed undo and try again. When you're programming and you're debugging something, a common thing is something's not working because you discover this by setting up some little test. You try, it doesn't get the right answer. You make a mod to the symbolic, you recompile, you do this cycle, and you look at some output, and you know it may be right or wrong again, and so on. And that cycle takes minutes. We have in mind that a programmer using this software Redux stuff, that the system could do things like that itself at rates as high as 1 million such cycles a second with the hardware support we're talking about. So these are more details as to how it's done. Okay. The point about computer consciousness is it is an AI project. There's no two ways about that. But the AI technology needed is much like what's needed for chess, and the similarities are really interesting. So the rest of this is just some generalities here, but I want to elaborate a bit on why it's similar to chess. Chess was called by John McCarthy the Drosophila of artificial intelligence. You know, Drosophila is this little fruit fly that reproduces very fast, and it comes in different varieties with, you know, maybe the eyes are a different color, this, that, and the other. And it was very useful for research in genetics and so on. Well, chess is the first problem that lots of people thought could not be solved. That is a kind of high-level human intellectual activity where the computer finally got to the point of being better than anyone. What was interesting to me always is that everyone poo-pooed computer chess as long as there was at least one person on Earth that could beat it, you know. That wasn't intelligent yet. That shows where the rest of us are, you know. You have to think about what was the innovations that really let this happen. And it really started out with, I was involved in some of this, and so I can give you an insider's viewpoint. I was involved sort of peripherally in activity at MIT in computer chess, and then we heard about a program that came out of Carnegie Mellon, I think it was called TECH. And TECH had a new algorithm. It didn't pay any attention to trying hard to evaluate the board as to whether you had a good position, control of the center, whether you castled yet, or stuff like that. Instead, it just counted up material. You know, you see, what do I have? You know, a queen is worth so many points, a rook is worth less, bishop and knight are worth less than that, and then the pawns are worth 1 point each. And you just count up yours, and you count up your opponents and see who's ahead, whether things have gotten better or not, or worse. The other thing you do is to look ahead. This is, you say, okay, what moves could I make from this position? Then for each of those, what moves could my opponent make? And then so on. And they invented a strategy called mini-max. And then that was long ago from game theory, and John McCarthy pretty much dreamt up what's called alpha beta, a heuristic, and that had an amazing result. Alpha beta let you go twice as far down the tree, and that's a lot with an exponential search. Okay, so at MIT, you know, they worked hard on evaluation, they worked hard on everything else, and they had a certain level of performance. These guys at Carnegie worked hard on move generation and sort of ignored evaluation and just used material. The only thing they did a little funny is when they got to a position at the end, they looked to see if there were any captures possible, and they let all the captures happen before they counted up the material, which was, so they explored what we call the capture-free fringe of this tree. Well, the program worked surprisingly well, you know, and it's sort of ignoring all the work that other people were doing and so on and so forth. And then this guy, I don't even know how to pronounce his name exactly, Shu, I think it is. What?
He calls himself CB, right?
CB?
Yeah.
Okay, right. He was a student there, and he had the idea of making a chip. This was an idea that occurred to me, well, not a chip, occurred to me to make a computer that had a hardware move generator, and actually it was built at MIT, and strangely, due to various strange politics, it never was programmed. So, in any case, this tale is pretty important. The chips were made at Carnegie, and they made a computer that did very well, and that project made a lot of progress and got into the master class and so on, and eventually got transferred to IBM and was pursued, supported financially by IBM as a kind of publicity stunt, but it was good research, and they, of course, got to the point where they were able to play world champion level chess and beat Kasparov in a match. And the point was, they had a lot of hardware, you know, close to 1,000 specialized big chips doing move generation and so on. And that solved that problem. Okay, the chess problem. What is the chess problem? There's this chessboard. It's, you know, it doesn't grow. It's not anything different. It's a simple 8x8 square. And then you have these pieces. There's only a few pieces. The rules are very simple. This is not something like understanding literature, understanding English. It's a completely different problem. It's a very simple problem, but complicated because of the combinatorics and so on and so forth. Now, all kinds of people in the world work on AI, and a lot of them work on natural language understanding. This is probably the hardest problem in AI. They don't get very far, as a rule. Okay, so what I claim is that there is a problem in the software Redux area that's just like chess, where everything is 100% perfectly defined. And I'll give you an example. It is this. Say my task is, I have a program that runs in some language on some computer, and I want it to run on some other computer. Okay, maybe it's running on an Intel, and I want to run it on a Power PC, a Mac or something, who knows what. Okay, now say it's written in C code. Here's what's exactly defined. I have this C code. There's no problem interpreting it. I mean, you know, understanding what it means. And there's a compiler. The compiler is this algorithmic deterministic thing that changes this into binary code, right? When I look at the binary code, there's no problem understanding what every single thing in it means, because we know it's defined by the computer, and the computer is a deterministic machine also, and so on and so forth. Now, what I want is I want the symbolic code on my new machine to work. If I'm lucky, it'll work on the first try. If I'm unlucky, it won't. Okay, but now imagine this thing I call Programmer's Workstation. What it is it's a tightly coupled, specialized system that has, say, a central machine, which is the one that runs the software for this Programmer's Workstation. And then it has the source program, if you like, machine sitting there. And it has the target machine. And these are all tightly coupled where we can communicate fast, and it can be all, everything that happens is under control of the central machine. And so somewhere I have a picture of that, which I'll get to. I'm going past this stuff. Okay, this is stuff I've talked about. Oh, here's one funny thing. I'm trying to explain why this is important. according to the Bureau of Labor Statistics, and who knows where they get their information from, this is how many people are working places. And here's how much they're paid according to them altogether. If you do the division, you'll discover that you're all grossly overpaid by the Bureau of Labor Statistics standards, because this comes out to pretty low pay per person. Anyway, $150 billion a year is spent, is direct pay to programmers, according to them. My only point is most of those people are doing this software Redux stuff. So it could have a big payoff, is the point of all this. Okay. So let me, this is sort of supporting some of what I've just been saying. I'm going to race through that. Okay. So here's what I'm talking about right now. Software Redux doesn't have to deal with anything ambiguous or meanings or interpretations or anything like that. Okay? Makes use of clearly defined knowledge and so on and so forth. The point about, this is more of the points I just talked about with chess. And here's about Deep Blue. I should have looked at my slides here. Okay. So, right. Deep Blue did beat Garry Kasparov, and Mr. Xu is here at Microsoft Research. I think he's in Beijing, isn't he? Yeah, okay. Okay. So here's this other point I mentioned before. Deep Blue was possible because something that's stupider than any chess player at one aspect of chess, but amazingly faster than even the world champion at another, and you put those two things together, blinding speed with, you know, just mediocre ability to evaluate things, and you can beat the smartest person in the world. And this is because we're dealing with a particular constrained system. Okay, so with Software Redux, we're trying to do the same kind of thing, as I was saying. So actually rewriting code from one CPU to another can be an exact process. But, you know, it's not simple. And IBM had a horrifying experience as a corporation where, here's something you may know, but I think hardly anyone in the world knows this. You recall that Apple migrated itself from the 68,000 to the PowerPC. And you may know how they did this. They made an emulator, which is a completely bulletproof thing to do because you can emulate a computer exactly. The only trouble is emulator runs slow. And then what they did is, you know, using some performance evaluators, their version of vTunes, if you know what that is, that's Intel's a performance evaluator, if you like. They looked to see where things spending time in the OS and so on, and they hand-coded all that stuff, you know, or translated it to PowerPC, and then they released this to the public, and as time went by, they and the other vendors of software, you know, worked to migrate to PowerPC code, and I think they did that pretty successfully. What you may not know is that IBM and Apple worked together, and they hatched a plan together. IBM's plan was to migrate all PC software to the PowerPC, all Intel software. And what they did was they had what they thought of as a much more sophisticated approach than Apple had. And it's true, it was more sophisticated. Their idea was to take a binary from Intel and look at it and produce a binary for the PowerPC just directly. Okay? And it succeeded and did the right thing for about 99.999, or I don't know how many nines, % of all instructions. Okay? But it didn't succeed for all instructions and all kinds of weirdness. The guy who gave a nice long talk that I attended, who explained, he whined at the podium for about an hour, explaining all the difficulties he had. But my favorite thing was the following code example. This is only appreciated by a programmer, but, you know, some programmers write code that's meant to be a joke. it works, but the only reason they wrote it that way is if some other programmer looks at it later and figures it out, he'll laugh. Okay, so here's an example of code. The Intel platform has instruction prefetch that dates back to the 8086, the prefetch buffer. Okay, here's an instruction. It's indexed. So if you just look at it, you don't know what it addresses. When it's running, it's addressing the very next location, and it's a store. So this indexed instruction stores into the next location. Of course, what's executed next is not what was stored into there, but what used to be there. Okay? So there's no way the analysis program knows it's trying to do this trick, okay, when it looks at the binary code, because it can't figure out what the address is actually going to be, and so on and so forth. So that was one bug that just drove them completely nuts, because various programmers did that. There's never a reason to do it, but it was there in code. Okay. So the point is that the kinds of systems I'm talking about can examine code, watch them while they run, and so on, and figure out that this is happening, because you can monitor the code while it's running, and I like to call it this way. I have these two systems, and the third one's watching them, okay, and I have this system running the old code, has its finger on the old symbolic, say it's C code, okay? It has its finger on the running binary and the state of the registers. It's all watching all that. The other one is running the new code, doing the same things, watching it, okay? It has information as to the meanings of things and to the types of data and so on. And with all that, it can help the programmer a hell of a lot more than the programmer gets help today with some debugging system. That's what I think. And part of the tricks it has is, like the chess program, it can do experiments. It can do sort of look ahead. If it has an idea about something and it wants to try a number of possibilities, what I've figured out with the hardware support I'm talking about, given an execution of 1,000 instructions, and where one step is this: I make a modification to data or instruction or something, I then restore the system to its initial starting state, I run it with the modified, I look at the results, okay? It can do, that's what a programmer does, and a programmer takes a few minutes to do a cycle like that, okay? Here, with the hardware mods I have, a conservative estimate has it can do that process at 1 million cycles a second, 1 million full cycles, okay, per second. So it runs the whole code of 1,000 instructions and gets that done that fast. You know, you can see that as long as you're dealing with some high-level knowledge as to what is likely to be wrong, or you know, this same process running 1 million times a second can be used for exploring the reliability of the program over a range of variables. You know, when a programmer checks a program out, you know, he very often just, you know, sticks something in and sees if he gets the right answer. When he gets the wrong one, you know it's wrong. When you get the right answer, you don't yet know it's right, do you? All you know is, well, it wasn't wrong. But that's usually enough for most programmers at that point. They just consider the odds that it's still wrong and giving the right answer is very small. They're correct, but occasionally there's a problem. So this kind of thing can do a lot better on verification and, you know, that kind of thing. So here's a little more comments about that. So here's this review of these other things I've mentioned. All the stuff about having your finger on this, that, and the other. It turns out I found applications for this concept where you need maybe up to 5 computer systems all hooked together. And where that comes up is if we're just taking code from one platform to another, but it turns out in both cases the code is using a cross-compiler. In other words, I'm compiling on system A for some. This might be quite common if you're writing something for the Symbian or, you know, Palm Pilot or something like that, where your compiler is on another machine, but you need the ARM or whatever it is that runs the you know, the PDA code or cell phone code or something like that. So you might have as many as 5 systems all coupled together in that. Okay. So understanding code, in my opinion, involves, being able to figure out what the purpose of things is. And you get that purpose by being told a lot of information, sometimes by the programmer and often by watching what's going on and so on. So here's my bottom line point. There's workers all over the place working on understanding natural language, okay? That task totally dwarfs the problem of understanding computer code. And, but not very many people are working on this latter one. And what I claim is it's fantastically easier than understanding natural language, but it's still hard. But we could make a lot of progress in understanding code. And if we understand it in all of these different ways, then there's lots of things we can do and make things work better. Okay, so yeah, there's all these things. You have all these engines or CPUs and compilers, OS, and so on and so forth. It's very broad. Thousands of variations on all kinds of things, but it's not very deep. Natural language is broad and deep. Okay. So this is more on what that programmer's workstation looks like, and I have a little picture here, shows you I imagine making use of large FPGAs so that that central machine there can specify all kinds of conditions that are checked without having to have an incredible amount of pre-built hardware in it. Okay. So to make systems like this work along the way, you have to build yourself a library where you have knowledge of all these kinds of things. And, in talking to IBM about this, this is you're the first computer company or software company I've come to talk about this stuff. Okay, it's the first talk outside of CMU. Then my next one will probably be at IBM. And it's an interesting place for the following reasons. One is there will be some people at that talk that are into the PowerPC because, IBM designed the PowerPC and so on. But IBM has a particular problem, which is COBOL. It's not so much a problem because it makes them loads of money. It's other people's problems. But IBM is the largest worker in the field of helping companies that are living with COBOL applications that they can't escape from, as it were, easily. And, SAP has some ancient legacy systems that are driving them nuts, that they're trying to keep alive for customers, and so on and so forth. So that's sort of a lot of the motivation for this programmer workstation, is dealing with a lot of old stuff and needing to bring it into the modern world and so on. So this stuff should be good for everyone who creates or uses software. That includes a lot of people, like software companies, people who have big software, Department of Defense, government agencies, and Fortune 1,000 companies, and so on, programmers, users of software. Then this stuff is, well, I see some big project. This is not the kind of thing that some guy can go off and work for a year or two and get done, because it's broad. You have to deal with so many different things. But the big problem, of course, is to solve the first problem is to solve the intellectual issues as to how you do all of this, and then you have to make it happen. So I want to see such a project started, and we don't even have a plan at this point, but I'm going to go around and talk to people like here and see whom I can get interested in it. So that's pretty much the talk. Okay. So, yes?
trying to understand the connection between the machine understandable comments and the purpose of the code. The purpose for me, I'm trying to understand the connection there.
Okay, well, the idea of purpose is that when some action takes place, and let me give you just two extremes of this. One is the user clicks on something, and the other is that a subroutine call happens, okay? There's something in mind, that could be in mind, as to what is expected to be accomplished. My idea is that if you want to make progress here, we have to find some kind of language. I'm just thinking of these comments, but basically some kind of language, machine understandable language, where you can describe what this is that should happen. So for instance, we want the computer to know how long this should take, because we care if the right thing is done, but it happens for some weird reason to take 10 times longer than it should, okay? That's one thing. We also know, if we know approximately what's supposed to be done, we can tell if there's some kind of gross problem. I mean, you see, if I click on the icon for something and I expect something to come up on the screen, it could come up on the screen and something bad has happened anyway and it won't work. I don't know. Or, so the fact that it came up isn't enough, but if it doesn't come up on the screen, then, I know something's wrong. So what we want is to be able to have this internal thing that's conscious of what's happening, be aware of if the user does X, I should see Y happen within this much time. And if not, I should be able to figure out why not. That's the idea. Does that make? Okay. Yes?
I'm confused by your statement about that understanding computer code might be a little easier than understanding natural language. Mainly because if you take all the devices and input devices and output devices into account, computer code starts to get much more complicated.
Okay. You see, let me state that a little more modestly. Do you agree that understanding a computer instruction is easier than understanding a word in English?
Yeah.
Okay. So individual instructions we could understand. Now, you also can agree that a lot of little subroutines are just versions of instructions they didn't bother to put into the computer. They have very simple functions. For instance, it used to be that floating point was done by subroutines. Okay, so a lot of small subroutines are just like instructions. There's simple, well-defined task we want done. They don't happen to have an instruction for it. So you can agree there. Okay, and then you see, we don't have to have complete and perfect knowledge when we say understanding. If you say, yes, I understand physics, well, that doesn't mean you understand everything about physics. No one understands quantum mechanics, as Feynman used to say all the time. Okay, so the point is, as it gets more complicated, our information stops being quite so definite and perfect. If you said to me, what would it mean for this consciousness program to understand something perfectly and exactly? Well, all it needs is a model of it, a digital model, a little subroutine that, if I have a subroutine that does the same thing as an instruction, then, I can, understand the instruction in some other machine because I have a subroutine here that will do the same thing. I can, So what we do is we make up understanding out of little parts. And some things we understand exactly and completely, and some we have some knowledge of that's not complete. And the idea is to make use of this hierarchy of knowledge and such to make things go better. That's the idea. It's not, there's no magic in this anyways. That's the whole point. Just like there's no magic in the chess program.
Well, I suppose the reason why I'm asking is because it's my impression that most of high-spending software Redux, code maintenance, that sort of thing, is dealing mostly with problems, devices, and bits about and things like that.
Yeah.
So I'm wondering how much of this really lies here.
Well, you see, I had a wonderful experience lately where this is where you make lemonade out of lemons or something like that, in that since I've been interested in this, when something bad happens to me, I open my eyes and say, hey, I got to watch this closely. Where I had to download something, a database into a GPS, and it had a serial interface, and my computer had a serial interface but no serial connector, you can believe it. This one here, the connector's in the dock. And but you can get serial out the parallel port, or there's USB to serial things you can buy. I have one of them in my bag here. Okay. So 16 hours of work later, I managed to finally make this work with long conversations with Microsoft and IBM, both, neither helpful. The difference was the Microsoft one took much longer because and they ended up giving me a bunch of URLs to various websites that might help me. The IBM ones were useless completely. You know, what I ended up doing was, you know, I ended up finding software that printed out a complete, everything heading for the serial port. This gave me a complete dump of everything headed that way. You know, but I couldn't tell for sure if it was getting out the serial port. With computer consciousness, what we want to do is we want to have the system able to look at the outputs of the ports so that it can see that what's actually going out there and stuff like that. And, you know, let me just say what solved this problem was, you know, I had all the literature downloaded from the GPS company, Allied Bendix King, which is now, I think, owned by Honeywell. I don't remember who. Anyway, so just to tell you how this ended, you know, I started to play, well, maybe X on, X off has something to do with this. It says here it should be 8 data bits, 1 stop bit, and odd parity. So in desperation, I started fiddling with that. And I found a combination with none for the parity, and it downloaded the database. And part of my problem was I was in Reno, Nevada with my airplane, and early on in this process, it started communicating and then stopped. The result was that it zeroed out the memory of my GPS. Now, it's very different to have a GPS whose data is a month old, which means 99.999% of everything is correct, with one that has nothing in its memory. And when I turned it on, the first thing it said, what's the magnetic variation here? You know, because it didn't know anything. So I was really desperate, and I kept at this. And it was a random search. I'm not that organized. I didn't write things down. I said, I'll try this, I'll try that. And, okay. But some program could have done this better than me, and it probably could have gotten it done in a second or two. Yep.
There's a recent case in hand. There was a bunch of software that was well understood by the people, well understood by the computer, all the Cobble Brigade, payroll, and such like, and then somebody mentions data in the 21st century. I don't know how many hundreds of millions were spent on fixing that.
Well, first of all, I have to tell you one thing about the that particular bug, Y2K bug. I never believed it was a big problem. I believed that this was a giant scheme similar to everyone being spammed in some sense. And it was played up. A lot of people made a lot of money. And, you know, it wasn't the end of the world like people thought. There were some people who did nothing, and not all that, you know, some bugs showed up and they fixed them. But it was quite a panic everywhere. And, you know, it was useful to many people to fan the flames, as it were. So, yep.
As you were suggesting, so that you memorize the state and you go a few instructions into the future and come back and try it.
Yeah.
Then, if you have only 1 or 2 of these things in a complex environment like machine with touch software, then these actually kill off all the software because they are capable of recovering from the error. But yet the rest of the software is not. Right now, if 2 processes collide, usually both of them stop. But if you have one which is smart enough to, well, let's say what it's doing is trying to find memory to use. So you go to some place and store some information, and then later it turns out that this information was overwritten. Well, that probably indicates that somebody else is using this place, so it goes someplace else.
Okay, well, I don't
it
have...
kills off the first one that was trying to use that, and then goes to someplace else, kills off the next one, and so on.
Yeah, I understand
so maybe
that.
everything has to be adaptive in order to even test this.
Well, what you call everything, I'm calling the operating system. This has to be a feature of the operating system. And one of the things that I figured out with the hardware mods that I'm talking about is something you can do that's quite interesting, which is you can have a universal undo that is capable of undoing basically as much as you want, as far as you want. It can do it grossly or selectively. In other words, we could unwind some program without unwinding the whole system and stuff like that. So this could be a property of the operating system instead of today where it's a property of different programs. So for instance, if you're using MS Word and you want to undo, you're in a very different position than if you go to PowerPoint or Excel and you try to undo. But it could be the OS. But I think you're right, is this thing can't live in a piece of software. It has to be the operating system, because just the points you mentioned.
But at the same time, if you're calling the biological analogies, then you really don't have the operating system there. It's really a bunch of little independent processes that somehow learn to live together.
Well, you know, the analogies are good to a point. I'm not, no one's very expert in what I'm talking about, and certainly I'm not. But my instinct is that, you know, the way one would start with this is it has to be part of an OS. Just, and, you know, someone could prove that wrong, I don't know. But, go ahead.
Well, one other question about, I just want to make sure I understand. When you talk about how in your vision, when you've got a serial output port, and also sensing what's actually going out over that output port, that's introducing another sensor, which is also, I'm not sure how much you would trust. And so, and in your, to use your example, you've got a docking station with a serial output. You want to know whether it's going out, whether it's a hardware problem. But if you have another sensor which is also going through that same docking station and it's reading nothing, do you know that it's where is it going?
Well, you see, first of all, let me just say one thing. I got involved in a strange project once, which was to try and make a system that makes fresh water from seawater. And, you know, so I started a company, I designed this plant, and we built some. And we decided to make these totally automated. One of the design rules was that any sensor could fail in any way at any time, and the system simply keeps running and just tells you this sensor failed, and it keeps running. And so the point is this. First of all, today, the reliability of hardware is insanely better than the reliability of software systems, okay? IBM, for a while, had a very interesting policy when you called them under warranty for your computer. You say, there's this problem with my computer. And this was an official policy, okay? There's this problem with my computer. It seems to be something wrong with the hardware. They'd say, oh, well, here's what you do. Just put this CD in your computer and press such and such, and if the problem's still there, then we'll fix it. What did the CD do? It restored the computer exactly to the state it left the factory in. Mm-hmm. Now, they didn't really explain this, but, you know, if you had any brains, you say, what about everything I wrote it in? Oh, well, you have to reload that in later. I hope you backed it up, and so on and so forth. And all your, you know, and so on and so forth. That was their policy, okay? And, you know, so the thing is that the hardware is very reliable. But I have in mind that you can use this kind of system where you have multiple ways to figure things out. The way we did it in the water plant, I invented something I called a phantom sensor. Here's where the phantom sensor was. It was a way to compute what each sensor should be saying. And so, for instance, most of the sensors were pressure sensors because there was a lot of plumbing, okay? And so if I have a pressure sensor here, well, somewhere else I have a pressure sensor. But water is flowing through this pipe. But I know the formula for the pressure drop versus flow. I know the pressure here, and I know the head difference between this sensor and that, and so on. With all that, I can calculate what this would say. So the point is, in a well-designed system, you should have a way of determining independently from totally different things by principle what something should say in more than one independent way, so that you can determine the hardware bugs. But the hardware bugs today are a tiny fraction. Okay, there's hardware incompatibilities and all kinds of things like that. And by the way, you know, the first thing I bought was a parallel to serial connector, which was almost 100% useless. I couldn't make anything work. Then I went USB to serial, and it had one light. I bought that at Best Buy. Okay, I don't like CompUSA, but when I went there, this is all with me wandering around trying to fix it. I found one with 3 lights. USB to serial, so I could tell if it was sending, receiving, and I forget what the 3rd light did. That helped a lot, actually. So my point is that, you know, when you want to understand a problem, what you really want is independent ways to get information, so that you can tell if your information is any good. In a process control system, to me, the stupidest thing on earth is a sensor, which they use all the time, which does this. It says, yes, the pressure is okay, or no, the pressure is too low. And it's set to something, okay? If you have something that tells you the pressure, then you can, by listening to it, looking at it, you can tell how healthy the sensor is, okay? And, you know, the system we built had all kinds of interesting features. When a sensor was going out of calibration, it realized that. It says, hey, this sensor is still good, but it's drifted out of calibration. Well, I don't have to ignore it completely. I just have to take that into account. And interesting enough, those plants were built maybe 16, 17 years ago. They're still running. And there are 2 little countries that get all their water from them. And that system worked. So, you know, you can make hardware systems reliable and able to diagnose the hardware failures. And that ought to be there. But the software end, it's not so much that people have made errors, it's that the complexity and the fact that, you know, you have just give you one more example. One day I bought an HP 4100 printer at home, stuck it at home, and I couldn't print on it with my computer. I tried everything I could think of. I finally called Hewlett Packard, and I get one of these guys who's got his database. You know, he asks you questions. He interacts with it. He finally says, do you have Mathematica 4.0 on your computer? I said, yes. He said, that's the problem. I said, that seems very far-fetched to me because I'm just trying to use MS Word and print on this. He says, that's the problem. Download such and such. I did, and he was right. I downloaded such and such, whatever it was, and now it worked. So, you know, who can you blame that on? I don't know. But that kind of thing is happening all the time. You know? Go ahead. Yeah, right. Okay.
How did you feel about Stephen Wolfram taking your ideas about basic physics on cellular automata and not giving you any credit?
Well, first of all, you see, in his own way, he did give me credit, and I'll explain. Steve, you know, I introduced him to cellular automata and showed him a machine running the cellular automata when he was, I think, he might have still been a teenager, I don't remember. And so on and so forth. And, you know, he told me he was writing this book. And he had a long history of avoiding giving people credit. So I had conversations with him where I tried to explain to him how much better it would be for him if he would give credit instead of, you know, his prior attitude was anything someone tells me that they didn't publish in a referee journal, I feel free to claim as my own because they're not playing the game of science right, and, you know, science makes progress by publishing, and if they don't do that, they don't deserve any credit. That used to be his philosophy. So he swore to me he was a changed man, and he would give everyone credit. So at the beginning of his book, he said, I've had conversations with people where I learned a lot, and so on. And then he had a list of, I think, 240 names, and I was there. Okay? So it's just, he has a slight personality problem there, and so on and so forth. You know, it's not that, you know, he has done a lot of original good thinking. this came up earlier where he insisted that he learned nothing whatsoever from Maxima, which was, where he got the idea to make his first, was SMP, I guess, his first version of Mathematica and so on. And so all the Maxima guys at MIT hate him. But, that's what he is. See, he's very, very bright, and he's come up with a lot of original ideas. I discovered in history that there were other people just like this, and I think it was Laplace who was infamous for never giving anyone credit. And there's some letters to him that from other mathematicians that survived where, he's being chewed out for, since he's thought of so many things and, he's done so many great things, why can't he mention when he's discussing someone else's idea and mention who it is and so on. So there's a historical precedent for that kind of problem. But, he is what he is, and that's okay. So, yes.
Are you planning to start with a toy version of it, or are you going to dive straight to the operating system that really is in use?
I think you have to start much more. No, I don't think. Well, let me just explain. I don't think we're ready for a toy version. I don't think we're ready for anything except to get various people together, start talking about this, and start batting ideas around, and say, hey, we can do this way, and someone may say, realize there's something wrong with that idea, or come up. This is a very early stage, and so I wouldn't even say we're ready to start implementing a toy version. I think that needs to be a lot of discussion, and maybe we'll organize some meetings where people can come and talk about this, and so on and so forth. So I see a project, and it seems to me to be way too big in a sense for some, like a group to do it by themselves, and where the interested parties get involved in helping to make it happen.
Thank you.